Hello, this is Jack Jackson, and today we're going to be talking about some more continuous probability distributions and how we can utilize the techniques we've learned earlier in this unit for these other distributions. So just more examples of what we have done earlier. Specifically, we're going to be looking at three different distributions, families of distributions: t distributions, chi-square distributions, and f distributions. In all three cases, there's at least a PDF function and a CDF function for these built into the TI graphing calculators that we're using. And in one case, there's even an inverse probability function for it, for the t distribution. So again, what we're going to be doing is applying the same kind of techniques we've done for other distributions, perhaps where I've given you a formula for the distribution. Here, instead of the formula, it'll just say something like t CDF or t PDF. So all three of these families of distributions are used extensively in our last unit on inferential statistics. When we get to that unit, we'll discuss how these particular distributions arise and what they're really used for. But only thing we're going to be doing in this unit is using these built-in functions where we know one is a CDF or a PDF, and use that to do different things. So some of the things that we've already done earlier that we're going to be able to do here in this video is maybe graph the PDF, calculate probabilities and shade the corresponding areas using the PDF along with our numerical integral or function integrate command. We'll graph the CDF. We'll calculate probabilities using the CDF, calculate cumulative probabilities using trace. And then we'll calculate inverse probabilities using the CDF, where if you remember how we do that, if we've got a CDF graph, we can graph a horizontal line at the probability we're trying to reach, the cumulative probability, calculate an intersection, and use that to find the x value that produces that cumulative probability. And if it's available, which it is in one case, with an inverse CDF, there is an inverse t function built in. We'll just use that directly, like we did the inverse probability function earlier. So let's start by looking at the t distributions. This is a family of distributions, and they all have these sort of characteristics in common. First of all, they're very, very similar to the standard normal distribution. In fact, if you just looked at one of them, you'd probably say, well, that just looks like the standard normal distribution. It's bell-shaped for the PDF. The mean is 0. The standard deviation on a standard normal, remember, is 1. The standard deviation on any of these t distributions is just a little bit bigger than 1, so they're a little bit more spread out than the standard normal. But other than that, they're very similar shape to the standard normal. And they're symmetric about the mean like the standard normal is. There's one t distribution for each value of a parameter that's called the degrees of freedom. The degrees of freedom will be a natural number. Usually it's at least 2 or 3, but it's 1, 2, 3, 4, a natural number. And where these are going to arise is later on they're going to have something to do with a sample and sampling distributions. So when we have a sample here, you take the sample size minus 1 to find the degrees of freedom. For what we're doing in this unit, we don't really care about it. I'll just tell you what the degrees of freedom is, what the degree of freedom is for that particular one, and we'll just use that. But later on, when we apply it, we'll know that the degrees of freedom is sample size minus 1. And so there's one distribution for each degree of freedom value. And the larger the degrees of freedom, the closer the distribution comes to the standard normal distribution. So you can think of this as sort of like a variation on the standard normal distribution. So now let's use our calculator to graph a t distribution. Okay, let's graph the PDF for the t distribution. So if we go to our y equals screen, put our cursor up there, clear out the other graphs, put our cursor up there on y1, y1 equals, put it there next to it, And if we press the distribution button, which we get by hitting the second button and the variables button, VARS button, we'll get this screen that's over here on the right. We've seen this many times before. We've used this to get the normal PDF, the normal CDF, the inverse normal. We used it last unit for binomial and geometric and so forth. And if we go down here, you'll see a T. There's an inverse T, number 4, PDF, T PDF, number 5, and a T CDF, number 6. So we have the full list of all three, just like we do for the normal distribution. And they work very similar to the way the normal distribution functions work. So if you remember how to do those for normal, you'll automatically know how to do them for the T. So except that the T always has a mean of 0, and rather than giving it the mean and the standard deviation at the end, what you do is you give it the degrees of freedom. So that tells you which T distribution it is. So if we want to graph a normal, not a normal, but a T distribution with 5 degrees of freedom, if we want to graph the PDF, we choose number 5 here, T PDF, and that comes up. That'll open a parentheses. We type in our X, comma, our degrees of freedom, which is 5, close our parentheses. The window that I've chosen here is very similar to a window I might use for a standard normal. -4 to 4 on the X, and -0.1 to 0.4 on the Y. And of course, really, you don't have to go below 0. I only go put that -0.1 there to give a little empty space at the bottom of the screen in case we want to do some kind of calculation on this later. And look at the graph. If you just looked at that, you'd say, well, that's probably a normal distribution. Very, very similar. So keep the window the same as on the previous slide, and let's have you do this one. Graph T distributions with 2, 5, and 15 degrees of freedom. This is 3 different distributions. Graph them at the same time on the same screen on your calculator. And then tell me what you notice. Compare and contrast them and tell me what you notice. So let's stop here for just a second. Let you do that and then come back. Press pause now. Okay, well, here's what we have. And what we find is that the larger the degrees of freedom, the smaller the standard deviation and the less variable it is. And so it comes in tighter. So this one that starts on the top out here comes underneath and is on the bottom here in the middle, goes up the least, and come back down. That's the one with 2 degrees of freedom. And then the one with 5 degrees of freedom is a little bit lower out here. They cross over each other here, and then it's a little bit higher right here. And comes back down again. And 15 is even lower out here, but then even higher in the middle. So notice that the bigger the degrees of freedom, the more area you have there close to the mean of 0. However, notice in all cases you do get a basic bell shape. You do get, as if any distribution, a total area of 1. This actually does theoretically at least go out from -infinity to infinity, although it's getting very, very close to the axis as you go far out there. Symmetric about the mean of 0. How does this compare to a normal distribution? So let's try this. Graph a single T distribution, how about one with 3 degrees of freedom, and then also graph the standard normal distribution. Graph those two together on the same window, and let's see how that looks. Go ahead and do that now. Press pause. Okay, now that you're back, hopefully you've graphed these two things, and you got a graph that looks something like this. We put in the normal PDF from X using 0 and 1, or of course you can just leave out the 0, 1. It'll default assume that you have a standard normal there, 0 mean and standard deviation 1. And then here's our T PDF with 5 degrees of freedom. And so the darker one, notice I've made this one bolder, is the normal. So notice the normal's a little lower here on the outside, but when it comes in the middle, the normal's up above. And so we see that the T distribution is a little bit more variable than the normal distribution. So the standard deviation is going to be a little bit higher than 1 for that T distribution. And if we keep getting that degrees of freedom higher and higher and higher, it starts to look more and more and more like the normal distribution. Now, graph a t-distribution PDF with 5 degrees of freedom on your graphing calculator, and use this graph to compute the probability that the t-value is between -2 and 1, or in other words, the x-value on their input value on the t-distribution is between -2 and 1 for this particular t-distribution, and also shade the corresponding area. Now remember, how do we shade areas if we've got a graph of a PDF? We can choose that calculate, I believe it's number 7, that's our numerical integral. Go ahead and see if you could do that now. Press pause and come back when you're done. Okay, so if we do this, we do calc, which is second trace, and press number 7, and we get the numerical integral, and it will shade and calculate an area, which is a probability for us, and it asks you for a lower limit, which is -2, and an upper limit, which is 1, and you enter those values. So once I hit second trace to get calc, and then press number 7 to get the numerical integral, then I make sure I'm on the correct curve, which I only have one here, so that was easy, and then push it'll ask for a lower limit. I type in -2, enter. It'll ask for upper limit, type in 1, enter, and then it will shade the area that we're talking about here and compute the probability, which is 0.76742153. Now, what if we want to do this on our calculator without shading? So here you see in the bottom left is the version we got from the shading version. We can actually go to our home screen and do function integrate, or the numerical integral, which is we can get by doing Math 9 from the home screen. Now, if you've got the older operating system, it'll come up FNINT, open parentheses. You type in the formula. You either type in tPDF x, comma, which will open parentheses, x, comma, 5, close parentheses, comma. Or since it's already stored in Y1, then I can just type in Y1 there by going to my variables menu and finding Y1. Then it's always x for the second input, and then it's lower limit, upper limit, so in this case -2, 1, and we get that same number we got over here before. If we've got the newer operating system, it's the same numbers, it's written more like you'd write it by hand. It's an integral symbol. That's just this long, skinny S standing for the sum of this accumulated area or accumulated probability. And the lower limit goes on the bottom here, the upper limit goes on the top, and the function goes in here, either Y1, since we know we have it stored in Y1, or if we don't have it stored in Y1, or we just rather type it out, we can type it out as tPDF, which again comes from your distribution menu. Second variables will give you your distribution menu. Find that in the list and choose it, and it's x, comma, 5, close parentheses, so this is our input function, and it's always x here for the integral, and so we work that out and we get exactly the same answer. So if you really just need a probability, this is one way to get it. Actually, not the easiest way. We'll show you another way in a minute. Now let's go on to the CDF and see if we can graph that. Now remember, the CDF is built in, and I will give you a hint. It works exactly like graphing a normal CDF, except instead of giving it the mean and standard deviation at the end, you give it the degrees of freedom. See if you can go ahead and do this one on your own. Graph a t-distribution CDF, cumulative density function, and with 5 degrees of freedom, and see if you can go ahead and do that for a t-distribution. Press pause now. Okay, well, we come back and we see that we can just type in tCDF, and just like a normal distribution, you have to give it left input, right input, or left limit, right limit, and then degrees of freedom is the part that's a little different than the normal. Now, in this one, in a normal distribution, I told you about 10 standard deviations of work. This one's a little more variable, so I'm going to go out a little further. I'm just going to go out to a negative 1,000. Technically, that should be what? Negative infinity. But we can't really put in negative infinity on this kind of calculator, so negative 1,000 works pretty well. Okay, so we'll use that, and we'll use kind of our standard thing for the window from negative 0.1 to positive 1.1. And then I went from negative 6 to 6. And if you do that, I went ahead and made that one darker. And I've got the PDF graph too. So the PDF was this kind of pretty much bell-shaped curve underneath. And the darker one is the CDF. And what would we expect from any CDF? It starts at 0 and ends at 1. Just like a normal distribution, this actually has an asymptote of 0 and an asymptote of 1, but without ever actually technically hitting it. But, of course, it gets extremely close at some point. Okay, so now use the CDF function to compute the probability that t is between negative 2 and 1. Again, with 5 degrees of freedom. Well, we can do it from the graph this way, this series of these 4 smaller windows here. If we've got the graph going, we can trace. And we trace it at the right input at 1, and we get a probability of almost 82%, 0.81839 something. Now that's a y value, so if I immediately go to the home screen and type y, alpha something for y, then I get this here to come up. Now if I trace this on the CDF again, but do it for the negative 2, so my input's negative 2 and my output is 0.05, I can say take my previous answer, subtract this new y, and the difference between the two, so if I take the 0.818 and subtract 0.051, I get the 0.767. And so that is my probability. So if you have a graph of the CDF, that's what it means. It's the difference, the cumulative, or the probability between 2 points is going to be the difference between the y values of those 2 points on the graph. Now, of course, it's a lot easier than that to actually compute. All you have to do is go to the home screen and do TCDF, left input, right input, degrees of freedom. And so it's really easy to compute probabilities like that for a t-distribution. And notice when I do this, I get many, many decimal places of accuracy. Now, how about inverse probabilities? So use the graph of the TCDF function for this particular t-distribution with 5 degrees of freedom to find b, where the probability that t is less than b is 0.72. In other words, notice we have the cumulative probability, and we want to find the corresponding t value or x value. This is like a problem we've done before, so you should know how to do this. See if you can do this on your calculator. See if you can figure out how to do this before you go on. Press pause now. Well, hopefully you remembered that when we have a CDF graph and we know a cumulative probability, basically we're saying we know a y value and we want to find the corresponding x. If we know an x and want to find a y, that's just trace. But if we know a y and want to find an x, the way the calculator works, what you have to do is you have to graph a horizontal line at that y value. Well, the y value that we're wanting here is the 0.72. So that graphs a horizontal line, and then we just simply find where that crosses the CDF graph. So do a calc intersect, which gives you the intersection point. Of course, we know the y value is 0.72, and this x value is the b value that we're looking for. That's actually a t value on this t distribution. Some usually call the input t if it's a t distribution. Okay? Now, some of you on your calculators, if you've got an older operating system, perhaps may not have an inverse t. Okay, so if you don't have an inverse t function, this is how you have to do an inverse probability. However, if you do have an inverse t function, it works just like the inverse normal function works. You just input the probability, and but you have to give the degrees of freedom. So to do the same problem we just did, you don't get all the shading and all that, or the drawing and the graph, but you do get the number, and it actually works out very nicely and very easily. So if you want to do inverse t of 0.72, comma 5, the 5 degrees of freedom, we get the output there and find that our b value we're looking for is 0.62398, etc. Alright, so let's see if you've been following along here. I have about 7 different exercises for you to do. So what I'm going to ask you to do now is to pause it on this screen here in just a second. Get your calculator out and see if you can work out each one of these problems and write down what you did and what the answer is for each of these example exercises. And then when you get done, come back and we will check each one of these. We'll have a screen for each one of these problems. So get your calculator out and let's try these right now. Press pause. Okay, so hopefully you've been following directions and you have your calculator out working through this stuff. You'll learn a whole lot more if you have your calculator and try these yourself. So let's take a look at each one of these one at a time. So the first one, we want to know the probability that t is between two values. In this case, negative 1.2 and 1.7. That's really easy with the TCDF function. It's really set up to do problems exactly like this. So you choose TCDF from your menu. The menu there is second vars, which is the distribution button. Okay, so that's choose distribution, which is second variables, and then it's one of the first few there will be TCDF. Remember, we use CDFs to compute probabilities. Really, the only reason we ever use the PDF is if we want to see the graph of the PDF or we want to see the probability as a shaded area. Then we would use the PDF. But in practice, if you're just needing numbers, all you really ever need is the CDF. So that's what we're going to be looking at the most. So you do TCDF from left, negative 1.2, comma, right, 1.7, comma, degrees of freedom, 8. And there we go. So the probability we're looking for is about 0.80399. Alright, here's another one, very similar. Just change some of the numbers, but it works exactly the same way. Let's go on to the next one. What about the probability that x is less than negative 3.2? Now there's actually a couple ways you could do this. We can make use of the symmetry and know that the cumulative area is 0.5 up to 0, so we could do 0.5 plus TCDF from 0 to negative, that would work if this is a positive 3.2. Since this area is completely to the left, what you would do is it could be 0.5 minus the area between negative 3.2 and 0. Or we can just go ahead and just say, well, it's TCDF from negative infinity up to the negative 3.2 with 19 degrees of freedom. And what do we need to use for infinity or negative infinity? We'll use negative 1,000 for negative infinity and 1,000 for infinity. And that gives you a pretty decent approximation. There might be off a little bit in the last digit or two, but most of your digits should be just fine with that approximation. Probably all of them actually should be good. So from negative infinity up to negative 3.2, substitute a negative 1,000 for negative infinity. Similarly, if we want to find the probability that t is greater than 3.5, we can go from 3.5 to infinity, and again, we'll just use 1,000 for infinity. Remember, you always have this last thing that's at degrees of freedom. That identifies which one of the t distribution curves we're working with. Now, suppose we want to find the probability that t is less than b, and we know that that probability is 0.95. We want to find the b. Okay, that's an inverse probability problem, and since we have the inverse t built in, that's going to be pretty straightforward to use that. We do inverse t 0.95, comma, 18 degrees of freedom, close parentheses, enter, boom. Now we have our b values 1.73, etc. So if you don't have an inverse t function on your calculator, what you're going to have to do here is you're going to have to graph the t CDF, also graph y equals 0.95, and then do a calc intersection, and this should be the x value of that intersection. So a little bit more work if you don't have this shortcut built in. So it's a pretty nice shortcut if you've got it. So next one is the probability that t is greater than b is 0.90 for t distribution, 14 degrees of freedom. Find b, and so remember that the input of an inverse t function, like the input of an inverse normal function, is the area or probability to the left of that value. Well, if there's 0.9 is the area to the right, remember the total area is 1, so you get 1 minus 0.9 or 0.10 to the left. So what we're going to need to put in is 0.10, the complementary probability. So we have an inverse t of 0.1, comma, 14 degrees of freedom, and we get an x value or t value of negative 1.345. Okay, this is a kind of problem that we sometimes have set up for us in our next unit, where we have a t value between a b and a negative b, and it's 0.9 is that area between there. In this case, say we have 4 degrees of freedom. How can we find what that b value is? Well, we take advantage of what we know about the symmetry. Because it's symmetric about 0, that and our b and minus b are equally on the same distance from 0, one to the right, one to the left. That means that 90% is split into 45% and 45% on the left and right of there. And more importantly, that the complementary probability, what's left, is 0.1. And that 0.1 is split evenly into half of 0.1, which is 0.05, to the left of negative b, and the other equal amount, 0.05, to the right of b. Now remember, if we want to find b and use an inverse function, we have to input the probability to the left of b. Well, to the left of b is the 0.90 plus the 0.05 that's that's to the left of minus b. So add those together, we get 0.95. So a total of 0.95 to the left of b and 0.05 to the right of b. So we can just do an inverse t of 0.95, comma 4 for 4 degrees of freedom, and then that gives us the t value for b, which is 2.13. Now we're going to look at the chi-square distributions. This is a family of distributions, and degrees of freedom 1 is a little different, but most often we have more than that. And if the degree of freedom is 2 or better, they'll start at the origin, increase to max, and then decrease. They're all skewed to the right, and they're all defined for only positive values. So unlike the t and the normal distribution that go from negative infinity to infinity, this is a lot more like the exponential distribution we looked at, where it goes from 0 to infinity. Again, we have one parameter called the degrees of freedom, and again it's a natural number, and we get one distribution for each degree of freedom. So we can graph a chi-square distribution, say with 6 degrees of freedom, And so since the domain is only positives, or 0 and up at least, we we only really have a first quadrant graph. I've got some down here in the fourth quadrant just to leave a little space at the bottom. So I set my x-min at, well, I chose -0.1. I should have just chosen 0. It's fine. And then go to, this case I decided to go out about 20. Actually, it usually works out if you go out about 2.5 standard deviations. That works out pretty well. So let's see, 2.5 times 6 is about 15. So 20's, 15 to 20. That's a good upper thing for this. Or 2.5 times the degrees of freedom is what I meant to say. So we have -0.1 to 0.4. Turned out to be a decent looking graph here. The input is kind of what you might expect. You choose the chi-square PDF from your distribution list. Remember that's second variables for distribution, and just go down till you find the chi-square PDF. Input is x, a variable, and then I'm sorry, this is with 5 degrees of freedom that's graphed here. 6 is very similar. So now let's graph one with 5, 10, and 20 degrees of freedom all on the same axes, and then tell me what you think, what you see there. So let's let you do this yourself. So you'll actually put in the 5, the 10, and the 20 as the degrees of freedom, but this will be 3 different lines, y1, y2, y3, in your calculator, and graph them all 3 together. So go ahead and do that now. Press pause. So if we leave the window about the same as last time, and we do it with 5, 10, and 20 degrees of freedom for a chi-square PDF, we get these graphs. This first one that you see here, where it goes up faster and then levels out, and goes up a little higher, that's the lower degrees of freedom, the 5. When we get to 10 degrees of freedom, it's a little more spread out, so the maximum value here happens a little further to the right and not quite as high as it did for 5. And for 20, once again, the maximum is even lower and further to the right. But they all have this basic shape where it starts at 0, actually it kind of starts concave up for a little bit, has an inflection point, switches to concave down, maxes out, comes down, somewhere has an inflection point, flips back to concave up, and levels out to 0. So it goes at the origin, goes up, maxes, comes down, leveling out to 0. And that's basically what a chi-square distribution is going to look like. So for our next task, let's use the graph of one of these chi-square distributions. Let's say the one with 5 degrees of freedom. And let's compute the probability that the chi-square value, the x value of the chi-square, is between 3 and 6. And while we're at it, let's go ahead and illustrate that by shading an appropriate corresponding area as well. Go ahead and do that. Press pause now. Well, if you've got a PDF where you've got it graphed, so you let y1 be chi-square of x comma 5, and then graph it, you'll get this graph here. And then to shade this, we choose calculate, which is second trace, and we choose number 7, which is our numerical integral, or our area shader or calculator here. And it asks for lower limit, which is 3, and marks that here. And then upper limit, which we give it 6, and enter. And notice it shades from an x value of 3 to an x value of 6, and it shades between the curve and the x-axis, as it always does. And that computes that area to be 0.39376692, which is exactly the same as that probability. So again, areas under a PDF are probabilities. So let's do a similar thing here to find chi-square PDF with 8 degrees of freedom. Compute the probability between 5 and 10. You should be able to do this one now. Press pause now and come back. Well, instead of shading it, we can also do it directly from the operating system without shading it. Okay, so this time we're going to use the function integrate command. In the older operating system, or with the math print turned off in the new operating system, it looks like this. FNINT, which is math 9, I believe, and you give it the formula chi-square PDF x 5, and then your second input's always x, and then we lower and upper 5 and 10. Okay, in the newer operating system, or the math print turned on, the lower limit 5 goes here, the upper limit 10 goes here. The one that's always x is here at this run off the screen here, but it's d and then the x. And what goes in the parentheses here is your formula, which is the first thing in the parentheses here, chi-square PDF x5. So we can do it that way, and we can get it there. But there's actually an easier way to do it. We'll get to that in a minute. So let's talk about a chi-square CDF, and let's graph it. Let's do one with 5 degrees of freedom. Graph it along with the PDF that we have in there now. You should be able to do that. Go ahead and do that now. Press pause. So this is what it looks like here. So the PDF I've got in Y1, chi-square PDF x, comma 5. And the chi-square CDF operates a lot like the T CDF or the normal CDF, where the input is lower than upper, and just like the T CDF, the last input is your degrees of freedom. So the syntax is just like the T CDF, except it's different. It's the chi-square this time. So I used the window that I had here, and also made it darker by putting my cursor over here on the far left and kind of hit enter once, and that turns it thicker. And so the thicker one here is the CDF, and the thinner one down here is the PDF. What do we expect on a CDF? We expect it to start at 0, and the CDF does start actually at the origin, and then it goes, continues up here, and then levels off at 1. So now let's use that chi-square CDF with 5 degrees of freedom to compute the cumulative probability of x less than 8, or the chi-square value up to 8. What would that probability be? See if you can do that now. Press pause. Okay, if you've done this, when we are trying to compute a cumulative probability, that's exactly what a CDF does. So if we've got the CDF graphed, we can just do a trace, and it goes to this point right here. We put the input of 8. Of course, we know x is 8, and the cumulative probability that x is less than 8 is the 0.84 whatever. Now we can actually find that a little bit easier, and by using the chi-square CDF in a very similar manner that we use the T CDF or the normal CDF. Let's compute the probability that the chi-square value is between 7 and 11 for a CDF for a chi-square function distribution with 5 degrees of freedom. Go ahead and do that. Press pause now. So this turns out to be chi-square CDF. You just give it lower, upper, and then the degrees of freedom. And so this is the easiest way to actually compute probabilities, is with the chi-square CDF. Just like you use the normal CDF or the T CDF as well. In fact, it's exactly like the T CDF, except it's chi-square instead of T, but the syntax is the same: lower, upper, degrees of freedom. So let's figure out how to find B, where we know the probability that x is less than b is 0.1. Well, notice this is an inverse chi-square. Unfortunately, there's not a shortcut inverse chi-square function built into the calculator like there is an inverse normal or an inverse t. Okay, so if you had an inverse chi-square, you could use it here. But if not, we're going to have to do it another way. You should know how to do this. See if you can do it now. Press pause. Well, remember, what we need to do is graph this chi-square CDF, which I have here. So remember, it starts at 0, so it's 0 up to x with 5 degrees of freedom. That's going to graph the chi-square CDF. And we know the cumulative probability is 0.1, so we graph a horizontal line there and find their intersection by doing calc intersect. And we find, of course, we know the y is 0.1. That's the cumulative probability, and we want to find the corresponding x, or chi-square value, which is 1.61. So here's some exercises for chi-square distributions. There are 5 of these. I'm going to ask you to press pause here in just a minute. Work through all of these, write down your answers, and work through these and then come back and check them in a few minutes. So please do that. Press pause now. Okay, so let's take a look at these one at a time. So we want to find a cumulative probability that x is less than 6. The easiest way to do that is just do a chi-square CDF, go from 0 to 6, 9 degrees of freedom, about 0.26. Next, we want to go between 8 and 15, find that probability with 10 degrees of freedom, also pretty easy. Chi-square CDF, 8, 15, 10. That's about 0.49677. Now we want to find the probability that x is greater than 21. Okay, so we would want to go from 21 to infinity, but rather than trying to estimate at infinity, remember we do have a solid bottom point of 0, so we'll do the complementary probability from 0 to 21 and subtract that from 1. So this is probability that x is less than 21 is 1 minus the probability that x is, probability that x is greater than 21 is what we're looking for. That's equal to 1 minus the probability that x is less than 21. So that's 1 minus chi-square CDF, 0 to 21, 11 degrees of freedom, and that turns out to be about 0.03. Now we're going to compute the following. Probability that x is less than b is 0.05, and we have 24 degrees of freedom. Try to find b. Okay, so this kind, since we don't have an inverse chi-square built in, what we have to do is we have to graph the chi-square CDF. So that's chi-square CDF from 0 to x, 24 degrees of freedom. Then we also graph the part to the left, except I have the wrong problem worked here. This is 0.1. So instead of 0.05, this is 0.1. So that's off a little bit. And so this is with the number you see here at 15.658684. That will give you the probability to the left of that is 0.1. So I'll probably go back and change this to 0.1 on the slide in a little bit. What about if the probability to the right is 0.01? Well, that means the probability to the left is 0.99. So we graph y equals 0.99 along with our CDF, this time with 19 degrees of freedom. Calc intersect there, and we've got our x value of 36.19. Okay, one more family of distributions we're going to look at in this video. That's the F distributions. And the F distributions are very similar to the chi-square distributions. And again, they have positive value inputs. They basically start at the origin and go up and come back down, kind of like very similar kind of shape to the chi-square distributions. It turns out there are two parameters here, both called degrees of freedom. You got your degrees of freedom 1, your degrees of freedom 2. Actually, it doesn't matter which order that you have those. So if you have degrees of freedom are 2 and 7 or 7 and 2, it doesn't really matter. It's the same thing. And these again are going to be one less than the sample size. The F distributions come when you have two samples, and we'll talk about that later. But for now, you just need to know that they've got two different parameters. And so if we want to graph an F PDF, this blacked out part is actually F. So this is F PDF, and we give it X, and this is 20, 25, because our two parameters. And if you put the 25 first, then the 20, you get the same graph. So it starts at 0, kind of goes close to the axis for just a little bit, and then goes up and back down. Okay. So here we want to use the PDF and shade again to shade the area that corresponds to the probability that F, the X value on the F distribution, is between 1 and 2. You should be able to do this. Press pause now. So again, we want to use our function integrate. That's calc 7, I believe. And we ask for a lower limit of 1, upper limit of 2, and it shades and computes that area for us. Graph an F CDF. with degrees of freedom 20 and 25. Press pause now. Okay, hopefully you tried that on your own and came up with this graph here. You put in FCDF from 0 to X, 20 and 25. Again, if you put 25 first, then 20, it would be the same graph. Again, as always, starts at 0, goes up, levels out at 1. Use the CDF to compute the probability that F is less than 3. Go ahead and do that now. Press pause. As we come back, we see that we just have to trace. And when X is 2, so F is less than 2, the probability is 0.949. If we want to use the FCDF without graphing anything, it works very much like the chi-square or the T distribution, except that there are 2 degrees of freedom you have to put in. So it's lower, upper, and then your degrees of freedom 1, degrees of freedom 2. So FCDF 1, 2, 20, 25. So if you're computing probabilities, this is going to be much easier than going through all the shading and all that stuff. But if you need to see the illustration or would like to, we already have gone over how to do that. But if you're just computing probabilities, this is going to be your most straightforward way with an F. Okay. Since we don't have an inverse probability function for an F distribution, when we have a problem like this where we want to find the probability that F is less than B is, say, 0.99, and we want to find the F value or X value that goes with that, then we have to do it this way by graphing the FCDF with those 20 and 25 degrees of freedom. Graph a horizontal line at 0.99 and do the intersection. Of course, Y is 0.99. The X is 2.699. So that gives you an example of how to use F, T, and chi-square distributions, and it reviews a little bit about how we can use these basic concepts of the PDF and CDF to compute probabilities and the relationship among these different things.